Today we're going to talk about the solubility product. And the solubility product is a type of equilibrium, and it's actually in many ways simpler than some of the other equilibria that we've been dealing with, particularly the acid-base equilibria. And this initial slide kind of gives you an overview of what we'll be talking about. Basically, you have a very low solubility solid like calcium chloride, and it ionizes to form not calcium chloride, copper chloride. It ionizes to form copper ions and chloride ions. The solubility equilibrium would be written in this way, and we know that the solid is not taken into account, and therefore it simplifies to this just product of these two ion concentrations, which is one of the reasons why this is called the solubility product. So the solubility product, or KSP, is the equilibrium constant for the equilibrium between slightly soluble ionic solids and a solution of its ions. Now I'm going to show you 5 different molecules that have low solubility, and I want you to write first the ionic equation on a piece of paper, and then write what you think the solubility product would be for each of the following, for each equation. After you've done that, I will show you the correct answers on the slide. Now, if you haven't finished your work, stop the tape until you get finished before you look at the answers. So the first one is silver iodide. The second one is calcium carbonate. The third one is magnesium hydroxide. The fourth one is magnesium ammonium phosphate. There should be a 4 at the end of the O. And the fifth is calcium phosphate hydroxide. So write each one of these and then write a solubility product for each one. Okay, so here are the answers. Here's the first one. Silver iodide breaks down to form silver ions and iodide ions. The KSP would be silver iodide, silver concentration, ion concentration, iodide ion concentration over the silver iodide concentration, but because that's a solid, we don't take that into account. And so we just write it this way. Sorry, this is a better way of looking at it right here. The second one, calcium carbonate, calcium ions, carbonate ions. The KSP for that will be the calcium concentration times the carbonate concentration. The third one, magnesium hydroxide, is magnesium ions, 2 hydroxide ions. The KSP will be magnesium ion concentration and the hydroxide ion concentration squared. Magnesium ammonium phosphate is a magnesium ion, an ammonium ion, and a phosphate ion. So it's all 3 of these concentrations multiplied together. And the last is calcium phosphate hydroxide, 5 calcium ions, 3 phosphate ions, and 1 hydroxide ion. And you can see it's to the 5th for the calcium concentration, to the 3rd for the phosphate ion concentration, and then the hydroxide ion concentration. Now, pigments used by artists, particularly in lead-based paints, are generally not soluble in water, or sparingly soluble in water. And this is so that they do not wash away when it rains, especially if you're painting outside. Now, an example of that is the yellow pigment lead chromate, which has a solubility of 4.3 times 10 to the minus 5 grams in a liter. What would the solubility product of the equilibrium constant be for this? Well, first of all, you look at the solubility in grams per liter, and this has to be changed into a molar solubility, so in moles per liter. This then breaks into the 2 ions at equilibrium, and then you calculate the KSP from that. And so first of all, you have the equation that looks like this. The KSP is going to be the lead concentration times the chromate ion concentration divided by the lead chromate solid. We know that we don't have to take the lead chromate solid into account because it's a solid, so it ends up just being the product of the two concentrations of the two ions. The grams, 4.3 times 10 to the minus 5 grams, is divided by the molecular weight of 323.2, and this ends up being 1.3 times 10 to the minus 7 moles in 1 liter, or 1.3 times 10 to the minus 7 moles per liter, or molar. And that's the concentration for lead ion, and that's the concentration for the chromate ion. And so the KSP will be the multiplication of these two concentrations, or 1.7 times 10 to the minus 14. Calomel, or diatomic mercury chloride, it was used by physicians back in the 17th century as a medication. Now, as you may or may not know, mercury is poisonous. However, patients rarely suffered any problems because calomel was insoluble. With a KSP of 1.1 times 10 to the minus 18 for its solubility product. So what would be the molar solubility of calomel? And let's roll this up. Here we see, let me just do this again because it's easier to see. So we have Hg2Cl2 breaks down to form Hg2, 2 plus 2Cl minus. So the KSP for this is going to equal the product of Hg2 concentration and the chloride concentration squared. Now, if we start with I, initially we have some concentration of this and none of this and none of this. Now there's no concentration here, so you don't have to worry about that. The change is going to be X here and then 2X here. And again, we don't have to worry about that. And in equilibrium, it's X and 2X. And so what that means is that 1.1 times 10 to the minus 18 is going to equal 2x squared times x, which means that that's going to equal 4x. Now I already did the math up here above, so let me see what the answer was here. So you see it's 4x squared is equal to that, so x is 5.24 times 10 to the minus 10. So x here is going to equal to 5.24 times 10 to the minus 10. And that's basically divide both sides by 4 and then take the square root. And so that is the molar solubility of calomel, which is this Hg2Cl. Barium is also used in medical procedures for two reasons. First of all, it's very radio opaque. That is to say that traditional x-rays do not penetrate barium. And so if it's in a viscous organ like the stomach or the small intestine, which is what is shown here, you can see it very clearly. And it also shows up very nicely, these little ridges, because it fills in and it's very radio opaque, so there's a great deal of detail. And the second reason is that barium sulfate is very insoluble, and so it's not absorbed by the person, and it has no side effects to speak of. So now let's do a couple of other problems in practicing here. So the first one here The first step in the preparation of magnesium metal is the precipitation of magnesium hydroxide from seawater by the addition of calcium hydroxide, a readily available source of hydroxide. And the equation is shown here. The KSP is this 2.1 times 10 to the minus 13. If the concentration of magnesium ion in seawater is 0.537 molar, will magnesium hydroxide precipitate if enough calcium hydroxide is added to give a hydroxide ion concentration of 0.001? Well, how do you do that? Well, the way you do that is you calculate the KSP using these molar concentrations, and if the number you get is greater than the known KSP, then it will precipitate. If the number, however, is less, then it will not precipitate. And again, I've already done this up here. You see that the equation here is the MgOH2 forms Mg plus 2 times OH minus. So the KSP is going to be the magnesium ion concentration times the hydroxide ion concentration squared. You put the numbers in and you get 5.37 times 10 to the minus 8, which that number is significantly greater, to the 5th power greater, 100,000 times greater than 2.1 times 10 to the minus 13. Therefore, yes, it will precipitate. The second problem is shown right here. It says, does silver chloride precipitate when equal volumes of silver, 0.2 times 10, or 2 times 10 to the minus 4 molar silver nitrate, and 2 times 10 to the minus 4 molar sodium chloride are mixed together? Now, the combination of sodium nitrate is very soluble, so we don't have to worry about that. So here's silver chloride, forms silver plus chloride, and you have silver ion concentration and chloride ion concentration. Now it says that you have equal volumes of 2 times 10 to the minus 4 molar. Well, if you add equal volumes of that, then the volume of the silver ion will dilute the chloride, and the volume of the chloride ion will dilute the silver ion, each by 2. So that's why we have 1 times 10 to the minus 4 here. You multiply that together and you get 1.1 times 10 to the minus 8. The solubility product, which I didn't give in the problem but I looked up, is 1.8 times 10 to the minus 10. And again, this number is 100 times greater than this number. So yes, indeed, the solution will precipitate. Now, blood does not clot if calcium ions are removed from the plasma. Calcium is a necessary part of the clotting system. Blood collection tubes contain salts of oxalate, and the purpose of the oxalate is to bind calcium and prevent it from being in the solution. And the solubility of calcium oxalate, the solubility product, is 2.27 times 10 to the minus 9. At sufficiently high concentrations, the calcium and oxalate ions will form a solid which contains water bound to the solid. The concentration of calcium in a sample of blood is 2.2 times 10 to the minus 3. What concentration of ion must be established before the calcium oxalate will begin to precipitate? So what the question is asking is, if we know this is 2.2 times 10 to the minus 3, what concentration of oxalate has to be present in order for us to have a precipitate? In order to do this problem, you need a clean sheet of paper first. So we have calcium oxalate goes to form calcium ions plus oxalate ions. And the KSP for this is going to be the concentration of calcium times the concentration of oxalate. Now we know it's given that the concentration of calcium is 2.2 times 10 to the minus 3. We don't know the oxalate, and we know the KSP is 2.27 times 10 to the minus 9. Now if we divide 2.2 into 2.27, it's going to be approximately 1 times 10 to the minus 6. So the concentration of oxalate that will result is anything greater than 1 times 10 to the minus 6.